Good evening, all of you. So we will start the session. I think only few members are joined. No problem. Okay, today's session is sets, functions, relations. So we will discuss the important points with respect to the gate preparation. One second. Yes. So sets, functions, relations. So first we'll see what is meant by set. So we know that a set is a unordered collection of different type of elements. Okay. So why here this is unordered is there is no need of specifying the elements in the order. So we can specify in an unordered manner. Okay. But only thing is there should not be any repeated elements should not be there. And see here the examples are there like this. Set of positive numbers, set of planets, set of states, set of lowercase letters. So like this, I can consider the example for this. And whenever we are working with the set, we may use two operators or symbols that we can consider here. So that is what we can say about membership operator. So if any element is belonging to the set, then it is represented with belongs to. If any element is not belonging to that particular set, then I can say that it is not belongs to. Suppose here in this set, if 2 is there, 2 belongs to that particular set n. And let us minus 1. Minus 1 does not belongs to n. So like that, I can use this one. 1 minute. Okay, next we have the representation of sets. So sets can be represented in two different ways, either in roster or tabular form or set builder notation. So roster or tabular form means in this method we will list out all the elements okay by within the flower braces separated with comma like this, and a set builder notation where we are going to represent the property of the element within some notation. Okay, here what are the common properties that is there for all the elements that is represented here. Let us here a is equal to, if I want to represent for vowels, so a is equal to x such that x is vowel in English alphabet. Or if you see here the set of odd numbers, to represent the set of odd numbers I may use like this, x such that x less than 10, where x modulo divided by 2 does not equal to 0. So like that I can represent the set. And here this is of different types of sets are there. Here we can consider the sets like this, finite set. If you are going to represent or if it is possible to count the specific number of elements, okay, so then it is going to be treated as a finite set. Infinite set means if it is not possible to count the total number of elements in the set, then it is infinite set. And coming to subset, so given any two sets, okay, let us x and y are the two sets. So when we can say that x is a subset of y means, so if every element of x is present in the set y, then I can say that x is subset or equal to y. Let us say x is equal to 1 comma 2, okay, and y is equal to 1, 2, 3, 4, 5 like this elements. Now every element of set x is present in set y. Now I can say that x is subset or equal to y. And here how many number of such subsets are possible for the given set y? So that is given by 2 to the power of n. You need to remember this. And this is the example. Let us say x is 1 2 3 4 5 6, y is equal to 1 2. Now I here every element of set y is present in set x, so that I can say it is y is subset or equal to x. And see this example, x is equal to 1 2 3, y is equal to 1 2 3. Now here either x is subset or equal to y, or y is subset equal to x. But the thing is both the sets are same. Okay, even though they are subset to one another, they are not proper subsets. So like that I can consider this. Next one, what is the meaning of actually the proper subset? Okay, proper subset means it should be subset, but it should not be equal. Okay, it should follow the property of subset, but it should not be equal. So then I can say that that is a proper subset. Now, if you consider the proper subset, the number of proper subsets, okay, here it is a number of proper subsets that are possible is given by 2 power n minus 1. For given any set with n number of elements, the number of proper subsets are possible is given by 2 to the power of n minus 1. And here one more point is that between the two sets, if you count the number of elements, so number of elements in the set X should be less than number of elements in set Y, then only it is possible to have the proper subset. And here it is the example: X is equal to 1 2 3 4 5 6, Y is equal to 1 2. Now I can say that Y is a proper subset to X. Next one, universal set. So the set which contains all the elements with respect to a particular context is going to be called as universal set. And we can consider example as set of animals in the earth, or set of numbers, or set of for birds. Like that we can consider as an example for this one. Next, empty set or null set. So the set which does not contain any elements is going to be called as empty set or null set. So no elements will be there. And I can say that the cardinality of the empty set is 0. And we are going to represent the empty set with 5. Next one, singleton set or unit set. So if you consider any set which contains only one element, okay, if the set is containing only one element, then that is going to be called as singleton set or unit set. And this is the example, let us 7 less than x less than 9 means the element that is possible 8 only. Now it is going to be treated as singleton set or unit set. Next, equal set. So when we can say that the two sets are equal means if the elements of the two sets are equal, okay. So like here it is 1 to 6, here also 6 1 to. Order may be different, no problem, but the elements should be same in both the sets. So then I can say that the two sets are equal. Next, equivalent sets. So it is a different from equal sets. So what is the meaning of this equivalent sets means if the cardinality of the two sets are same, then we can say that they are equivalent sets. Cardinality in the sense the number of elements that are present in the set. Let us see this example: A equal to 1 to 6, whose cardinality is 3, and B equal to some 16, 17, 22, again whose cardinality is 3. So that the cardinality for set A and set B both are equal, that is 3. So that set A and set B can be treated as a equivalent set. And coming to this important point, a disjoint set. So two sets are said to be disjoint when we can say that property is if there is no common elements between the two sets, or there is no common elements within the two sets, then I can say that that particular two sets are said to be disjoint sets. Let us see this example, the previous 1 2 6 7 9 14. So there is no elements which are common to both the set A and set B, so that I can say that set A and set B are disjoint sets. Now here the property for this is, so for the disjoint sets n of A intersection B is 5. As there is no common element, it becomes null. So then what happens to this formula is n of A union B equal to n of A plus n of B only. So as why? Because this becomes 5. So that it is a formula we can get for that. Next, this is operations on the set that are possible. Okay, here we can do many operations on the sets. Let us see the important operation that we can be considered. Set union operation. The union of set A and set B is a set of elements which are both in set A as well as in set B. Okay, and it can be defined symbolically like this: A union B equal to X such that X belongs to A or X belongs to B. That means the element will be considered from set A or from set B, and we can represent like this. So this is the area that is representing that A union B. Okay, in the form of Venn diagram we can easily represent and understand that one. Next, set intersection. So there is set union and this is set intersection. So set intersection means it is denoted by this and symbol, and the elements which are belong to the both set A and set B. Okay, that is going to be treated as set intersection. Let us see this example 11, 12, 13, and this 13, 14, 15. The common element in both the sets is 13 only, so that A intersection B equal to 13. In the form of Venn diagram, we can represent like this. So this is set intersection. So one second, I will be. Please, sir. Okay, sorry for disturbance. So next we have set difference and relative complement. Let us see what is this set difference and relative complement. Okay, set difference or relative complement means it is a subtraction operation like that we can say. That is A minus B like that we can denote. What is the meaning of this is we will consider the element from set first set only and we will not consider the element from second set. So that means we will X belongs to A and X does not belongs to B. Suppose if you in terms of Venn diagram I can represent like this. A minus B means we will consider the elements only from set A and the elements from the set B will not be considered, and this is for B minus A. Again here the elements will be considered only from set B. Now here this the example where I can find out A minus B as well as B minus A. In most of the cases A minus B will not be equal to B minus A. So next complement of the set. So here it can be denoted as A dash or A bar like this, and here the elements which will be considered from what we can say that is universal set, and we are not going to consider elements from set A. Okay, we will consider the elements only from universal set, and those elements should not be there from what we can say set A. Then it is going to be represent complement of the given set, and this is in the form of Venn diagram. We can represent that one. Okay, so these are all what is the elements from the universal set, and these elements will not be there in set A. So next Cartesian product, or it is also called as a cross product. So given two sets or two, it can be defined for any number of sets. So given two or three number of sets, so we can generate all possible combinations from the set of elements first set to the second set. So that particular group of ordered pairs, whatever we have, that is going to be called as Cartesian product or cross product. Let us see this example. A is equal to AB, B is equal to 1, 2. Now I can generate all combination of ordered pairs A1, A2, B1, B2. Now it is going to be called as a Cartesian product or cross product. Next one, power set. So this is the set of all the subset for the given set is going to be represented as a power set, and it is normally denoted with the P of A. And for the given any set, the power set will contain the number of elements as 2 to the power of n. Let us see this example. Let us S is equal to A, B, C, D. We have the elements like this. Now we can write all possible subsets. Here the point is that null set is or empty that is empty set or null set is subset to every set, and the same set itself is subset to every set. And with the one element I can write A B C D, with the two elements A B A C like that, with the three elements like that. So like that, if we are all grouping all these values, all these elements, totally 16 sets are possible, as we have the set will contain, as the set is containing 4 elements, totally 16 elements are possible. So next one, important one, inclusion and exclusion principle. Okay, so it is a method of counting how many number of elements are there from the given two or more number of sets. Okay, so it is based on the principle or the operation called as a union operation, based on the sets that are given. Suppose if you are given with the two sets, it can be represented symbolically like this. So n of A union B equal to n of A plus n of B minus n of A intersection B, or cardinality, like that we can say. And the same thing can be extended for three sets. So a n of a plus n of b plus n of c minus a intersection b minus b intersection c minus a intersection c plus a intersection b intersection c. Here if you observe there, while counting for either two sets or three sets, we are adding some values or we are subtracting some other values. Why we do it like this is, so while considering set A, let us say if you consider this one, set A, set B, set C, okay. So there are some areas which will be counted for more than one time. Okay, so that what we have to do is we need to subtract them. So that's why A intersection B, B intersection C, A intersection C, and the common for three sets area, that is in the middle, A intersection B intersection C. If you are subtracting for every time, what happens? So this area also will be removed. So that what we have to do is we need to include this one. So that means here some of the values we are including, some of the values we are not including. So that's why the principle it is called as inclusion and exclusion principle, and it can be generalized for any number of sets. Let us see here, summation, it is summation of ai, I value will start from 1 to p. Okay, next minus, initially plus will be there, next for the next second time we'll get minus. Okay, here I1 I2, that is two sets with the two combination, will get again from 1 to p. So with the two sets we'll get minus. Again for three sets it is as usual plus only. Next for four sets we'll get minus. So like that alternative will get plus and minus, we can easily remember for any number of sets. So this is inclusion and exclusion principle. So let us see a small problem which is related based on this inclusion and exclusion principle. Let us, if you want to identify the set of natural numbers which are less than or equal to 1000, and they should not be divisible by 2 or 3. Okay. So now I can consider the numbers which are divisible by 2 as A2, and it is identified by 1000 divided by 2. So why I considered 1000 is the numbers are which are less than or equal to. Sometimes less than given means here we need to consider 999 only. Okay, 1000 by 2 500. Similarly A3 means the numbers which are divisible by 3, it is given by 1000 by 3, and as the two, it is a two sets, we need to consider the formula with the two sets. So a2 intersection a3, numbers which are divisible by both 2 and 3. Okay, so 1000 by 6 will get 166, and we substitute this, we will get the value 667. So what this value represent is, this is the total number of values which are divisible by either 2 or 3, but in the problem they are asking for the numbers which are not divisible by. So that what you have to do, this 667 need to be subtracted from the universal set. Universal set means totally we have 1000 values. From the 1000, if you subtract the 667, we'll get 333. And this is about the sets. So next we have the relation. So now we'll see what is this relation. Just 1 minute, I will be back. So next, see, this is with respect to the relation. What is actually the relation? Okay, so the set of ordered pairs defines a binary relation which is called simply a relation. So we in the previous sets we defined the cross product or cross product operation. Okay, so that cross product will generate set of ordered pairs from set A to set B. So that particular ordered pairs, if you are group them as one set, that is called as a binary relation. So if it is defined between two sets, then the relation is called as a binary relation. And here is the important point. So the number of relations that are possible from set A to set B is given by 2 to the power of n of A multiplied by n of B. So that means the number of elements from set A and number of elements from set B. Okay, how many relations that are possible for the given number of elements, that is A and is in the set B, it can be calculated by using this formula. And if R is a relation, a particular ordered pair, suppose x comma y belongs to R means, so now what we can say is, we can read it as x is in relation to R to y like this. And here is the example, a equal to 5 6, b equal to xy. Now the ordered pairs that are possible from these two sets is 5x 5y 6x 6y. Actually this is the cross product operation. Okay, so now based on this we can define this particular relation. So next, related to the relation, we have two important terminology, domain and range. So domain means the domain of the relation S is defined by this set of all first elements of the ordered pairs. So we've written previously ordered pairs. From all those ordered pairs, if you are going to group all the first element, that is going to be domain. Similarly, range means if you are going to group all the second elements from the ordered pairs, then it is going to be called as what we can say, that is a range of the given relation. Okay, and it is symbolically we can define like that. Domain means x such that x comma y belongs to S for some y. That means, so here we are going to consider the elements x from the set of ordered pairs xy. Okay, and this S is the relation. Similarly, domain range means we are considering the second element, that is y, from the ordered pair x comma y, which is belong to the relation. So next is this the example. Let us A equal to 3 4, B equal to 3 4 5 6 7, and if they are defined the relation from A to B, and the relation is given by 2 4 2 6 3 3 3 6 4 4. Now domain is given by all the first elements. So 2 2 3 3 4. So if it is repeated, no need to write. And coming to the range, it is 4 6 3 only. Okay, here we have 3 4 6. So that range is 3 4 6. And these are the properties that are related to your relation. So reflexive property, symmetric property, transitive property, reflexive and antisymmetric property. So if we have the ordered pair, or if the ordered pairs are in the form x such that x is relation to R. Okay, so if x is related to again x is related to again x means, then that is going to be called as reflexive, like 1 1 2 2. If you have the ordered pairs in this form like that, we can say that it is following reflexive property. And symmetric property means, so if x is related to y, okay, x is related to y, then we need to have the ordered pair y should be related to x. That means if 1 comma 2 ordered pair is there in the relation, 2 comma 1 ordered pair should be there in the relation, then it is symmetric property. Coming to transitive property, so if you have x is related y and y is related to z, then x should be related to z. Okay, that means this particular ordered pair should exist in the relation. That is 1 comma 2 or 2 comma 4, then 1 comma 4 should present in the relation. So this is a 1 2 2 4. So what will get 1 comma 4. So if it is ordered pair that present in the relation, then that relation is said to be following transitive relation. And irreflexive means, okay, if x comma irreflexive means we should not, it should not so this is for opposite to reflexive relation. Reflexive means x comma x or x should be related with x. Irreflexive means x should not be related with x. Okay, that means we should not have the ordered pairs like this 1 1 2 2. Such kind of ordered pairs should not present in that relation. And coming to the anti-symmetric relation, here it is a important one. Suppose symmetry, just I can say it is a opposite for this, that is in the symmetric relation what we are telling here, if 1 2 is there, 2 1 should be there. Here anti-symmetric means if 1 2 is there in the relation, Okay, then 2 comma 1 should not present in the relation. Suppose if 2 comma 1 is present in the relation means here we are telling that x equal to y. So that means 1 is equal to 2. It is not at all possible. So when it is possible means 1 comma 1 is there. So 1 comma 1 again. So then 1 equal to 1. So then only it is possible. That means for 1 1 2 2 3 3 like that it will be possible. So that antisymmetric means if x is related with y, if x is related with y means then y should not be related with x. So if that property is followed, then it is, we can say that it is following antisymmetric property. And given any set and given any relation on that particular set, we can check out whether these properties are followed or not. Let us see this. The set is given with 1 to 10 elements and the relation is given by x plus y equal to 10. So now between these 1 to 10 elements, we will consider the possible values whose sum is equal to 10. Okay, now according to that, we can write the relation 1991 2882 3773 4664 and 55. So if you add any these two values, you will get 10. Okay, now if you see this for this, okay, coming to reflexive, so 1 1 2 2 should be there. So that kind of ordered pair is not there. Only 5 5 is there. Okay, for other 1 1 2 2 is not there. So that it will not follow reflexive property. Okay, next coming to 1991 2882. So these kind of order pairs are there. That means it is following symmetric property. So x is related y means y should be related to x. So then I can say that it is following symmetric property. And coming to the another one, so if you check for transitive property, let us see here 1991 should be there. Okay, 1991. So 91, so 99 means it is there, only 11 should be there, but 11 is not there. Not only for that, if you consider for any, so that particular ordered pair is now kind of ordered pairs are not there, so that it is not following transitive property also. So it is following only symmetric property. Okay, so reflexive property is not followed, symmetric property will be followed, transitive, irreflexive also not followed. Okay, and antisymmetric also not followed here. So that is relate like that we can check for this. And next one, the important one, relation matrix. Given any relation, that relation can be represented in the form of matrix like this, which will contain the values as 1 and 0. So when we can say 1, when we can say as 0 is if x is related with y. That means if you have 1 comma 2 ordered pair, so then here I will write 1. If 1 comma 2 ordered pair is not there, or if it is not, no relation is there between 1 and 2, so then I will write it as 0. So what we'll do there is, so I will write the value. So let us 1 2 3, and here it is, let us a b c d. Okay, a comma 1 0. That means between a and 1 no relation. A comma 2, between a and 2 we have the relation. So like that we will fill this particular relation matrix. Now here, what is the advantage of this relation matrix? Why you can consider this one? See the properties here. From the relation matrix, we can easily check out whether the given relation is following some specific properties or not. So how we can check that one? Let us see here. If the reflection is relation is reflexive, then all the diagonal elements will be 1. So that means here 1 1 1 1 will be there. So that means 1 1 2 2 3 3 4 4 like that we will get that one. Okay, if all the diagonal elements 1 means, then I can say that it is following that is a reflexive property, but here it is not like that, so that it is not following reflexive property. Next, if your relation is symmetric, then the relation matrix is symmetric relation matrix. That means r of ij equal to r of ji. Let us see here, this is 1 2 3 4. Again you assume it as 1 2 3 4. So let us, if you have 1 comma 3 is 1 means 3 comma 1 should be 1. Next 1 comma 1, so that is there. So 2 comma 3 1. So 2 comma 3 is 1, 3 comma 2 should be 1, but it is not, it is 0. So that it is not following symmetric property. So like that we can check. Next, if a relation is antisymmetric and Rij equal to 1 means Rj equal to 0. It is also not following that property. Why? Because for 1 comma 2, 1 comma 3 and 3 comma 1. So 1 comma 3 1 means 3 comma 1 should be 0, but it is equal to 1 no. so that it is not following that one. So by using this relation matrix, one can check whether a particular properties are followed or not up to some extent. Next, similarly, graph of a relation. So by using the graph of the relation, we initially it will be given a graph, relation. From the relation, we can construct a graph. Okay, we know that the graph will contain set of vertices and edges. Okay, here the vertices are nothing but the values, are the element that are present in the set, and the edges will connect from one vertex to another vertex if they have the relation. Okay, let us see here this example. The set x is having 1 2 3 4, and the relation is given by x greater than y. Now if you see here, the vertices will be 1 2 3 4 only. Okay, now when we will connect an edge from one element, one vertex to another vertex, is if they have the ordered pair. Suppose 4 comma 1 is there, so that between 4 and 1 I will draw a line. Okay, 4 comma 3 is there, so that I will draw a edge. Okay, like that we can construct the this graph for the given relation. Again, by using this graph, one can easily check out for some of the properties. Let us see here how we can check for the reflexive property. Okay, if the relation is reflexive, there must be loop at each node. Loop means we need to have like this. Okay, so for every node, if we have the loop, then I can say that it is following reflexive property. On the other hand, if the relation is irreflexive, then there is no loop at any node. Okay, if there is no loop at any node, then I can say that again it is following irreflexive property. So here if you see this relation here, so it is reflexive. Why? Because for every node we have the loop. And if you see the second relation, it is irreflexive. Why? Because there is no loop at every node. Okay, similarly here we can check for the diagonal elements. Okay, so all the diagonal elements, so they are going to have one means, then I can say that it is following reflexive property. And all the elements are zero means it is we can say that it is following irreflexive property, like this. So next, similarly, other property you can check here. If a relation is symmetric, if one node is connected to another, then there must be a return arc from the second node to the first. Okay, so symmetric means we know already. So a is related, x is related to y means y should be related to x. Now according to that, if you have an edge from 1 to 2, we need to have the edge from 2 to 1 also. Okay, symmetric property. So here if you see this 1 to 2, 2 1, so it will be followed. Similarly 1 to 3 is there, 3 to 1 is there, so that I can say that it is following symmetric property. But whereas here that is not the like case that. Okay, so next, for antisymmetric relation, no such direct return path should be exist. That means if 1 to 2 is there, suppose if here if you see there 1 to 2 edge is there, sorry, 2 to 1 edge is there, but 1 to 2 there is no edge. 2 to 3 we have the edge, but 3 to 2 edge is not there. So that now I can say that it is following antisymmetric. So it is following symmetric property, and this one following antisymmetric property. And coming to the last one, transitive property. And it is not simple to identify whether a particular relation is following transitive property by using the graph. Okay, we need to check out manually. Okay, so that is regarding the proper graph of the relation. What is the importance of the graph? So next, we have different types of relations are there. Let us see here equivalence relation. When a relation is said to be equivalence relation, let us, if it is following reflexive property, given any relation, if it is following reflexive, symmetric and transitive property, then I can say that it is a equivalence relation. Let us see this example here, x equal to 1 2 3 4, and the relation is given like this, and we can construct either matrix or graph for the given relation, and we can check out whether these three properties are followed or not. Okay, here if you see this reflexive means what we need to have there is, so we need to have loop at every edge. So here we are having loop at every node, so that I can say that it is following reflexive property, or all the diagonal elements should be one. And the symmetric means, so if you have edge from 1 to 2, 2 to 1, we need to have the edge. So in both the cases we have that, so that it is following symmetric. Similarly, I can check for transitive relation also. It will follow all the three properties, so that it is a equivalence relation. Next, coming to the another type of relation, this is what we can say congruence modulo relation or congruence relation. So, what is the meaning of actually this congruence modulo relation? Let us, if you denote a set of alpha, let us I you assume I, which is going to be a positive integers, and m is going to be another integer. Now, if the relation is defined like this, x comma y such that x minus y is divisible by m, x minus y is divisible by m, so then I can say that it is a congruence modular relation. Okay, let us see this example here. 83 minus 13, so that is 70, which is divisible by 5. So now what we can say, so 83 and 33 are congruence, so they are following congruence modulo relation, and this congruence modulo relation also follows reflexive, symmetric and transitive properties like your equivalence relation. Next one, compatibility relation. So when we can say that a relation is compatible relation. So if it is following these two properties, that is reflexive property and symmetric property, only these two properties are followed means, so then I can say that it is a compatibility relation. So see here, this is the example. Let us set X is containing like a ball, bed, dog, let, egg, and we are defining the relation such a way that so they need to have a some common letter. If you consider any two words, they need to have a common letter. That is the relation that is going to be defined. So then I can check out whether these properties are followed or not. Okay, here if you say this, this particular relation will follow that particular property. Let us go for a small example for reflexive relation. So let us, you consider any two words, ball. So again, ball will contain same common letter. Dog, again if you consider dog, again it will have the same common letter, so that it will follow reflexive relation. And coming to symmetric relation, if you consider any two, so let us a ball and dog, or ball and let. Okay, if you see their ball, let, they have the common letter, and vice versa, let and ball, again they have the common letter L, so that I can say that symmetric relation also followed here, so that it is following both the properties, so that this relation is called as a compatibility relation. And coming to the next one, transitive closure operation. So which is one of the operation that can be applied on the given relation, and it is represented as r plus r to the power plus, which is equal to r union r2, r power 2 union r power 3, r like that. So what is actually this r square? R square is nothing but the that is what we can say composition operation between the two sets. R square equal r circle r. Okay, so if you are doing r circle r, then that is r square. R r power 3 means r square circle r. So like that we can do. So we will combine all those composition of all that particular relations, then it is going to be called as transitive closure of the given relation. Now if you see here, this transitive closure, uh, up to for how many steps you have to do. So up to r n is equal to Rn minus 1. That means R3, R4, R5, like that we can do. Okay. So whenever both are equal, Rn is equal to Rn minus 1, we will stop the process and will combine all the ordered pairs. Then that result is called as the transitive closure for the given operation. Okay. Next, partial order relation, or it is also called as partial order set. So if any binary relation, it is called as a partial order relation or partial ordering. So if it is following these three properties, the three properties are reflexive property, antisymmetric property, and transitive property. Previously, we told equivalence means reflexive, symmetric, and transitive. But whereas this partial order relation means reflexive, antisymmetric, and transitive property. If these three properties are followed, then that is called as partial order relation, and on the set which we applied this one is going to be called as partial order set, and we'll use this normally this symbol less than or equal to, it is just like less than or equal to represent your partial order relation. So next, this example that we can consider for that. Let us we will consider the property greater than or equal to relation on the set of integers. Okay, we'll consider integers 1, 2, 3, 4 like that. Okay, on the set of integers we are going to consider this one. Now the relation that is considered is greater than or equal to. So now if you are going to consider any element, so So it will follow reflexive property. 2 greater than or equal to 2, 3 greater than or equal to 3. So it will follow reflexive property. And coming to another property, that is anti-symmetric property, that should be followed. Suppose 2 greater than or equal to, sorry, 3 greater than or equal to 2 means, so it will be true, but 2 greater than or equal to 3 is incorrect. So if it is the case, then I can say that it is following anti-symmetric property. Coming to the last one, that is a transitive property. So if 2 greater than or equal to 3, 3 greater than or equal to 4 means 2 greater than or equal to 4. So that it is will be followed. So it can, we can say that it is following transitive property. So as these three properties are followed, the given relation is going to be called as partial order relation. So next one, has a diagram. Actually, this is a graphical representation for the given partial order relation. Any partial order set with the partial order relation can be represented by means of a Hasse diagram, by which we can easily check out the properties, and we can go with some other proper things also. Let us see this example here. P equal to 1, 2, 3, 4, 5, and the relation is given less than or equal to. Now if you construct the Hasse diagram, it will look like this: 1, 2, 3, 4, 5. So what is actually the meaning of this is, uh, 5, 4. If you see this 4, 5, 4 is less than or equal to 5. 3 is less than or equal to 4. 2 is less than or equal to 3. 1 is less than or equal to 2. So like that we can assume this one. Now actually there is a process to construct the Hasse diagram. Let us see the previous example what we given there. So now according to this property 1, 2, 3, 4, the property given, that is less than or equal to property, and the set that is given is 1, 2, 3, 4. Now according to that, first we will write the values or the ordered pairs like this. Now first what we have to do is, first we need to construct the relation graph according to the ordered pairs that are there in that relation. Next, second thing is, first we will remove all the loops which are there in the nodes. Okay, if we remove the loops, that it will be the result. And after that we will remove all the edges which will causes transitive property. Okay, the edges which are a result of your transitive property, they will be removed. So now after that, at the last, what we have to do is, here arrows will be there, all arrows are in upward direction, those arrows will be removed, and we are going to represent the Hasse diagram like this. And these are some more examples. Let us given x equal to 2, 3, 6 like this, and the relation is less than or equal to. So now the Hasse diagram can be drawn like this. Similarly, the other set, other one is 1, 2, 3, 4, 5, and for that the relation is given like this, and the Hasse diagram can be constructed like this. So actually matrix is given. From the matrix we can construct the relation, that is by means of ordered pairs. From there I can draw this particular diagram, Hasse diagram. And similarly, important one, this is uh, the Hasse diagram can be constructed based on the power set, on the set of three elements. Okay, so this power set will have all the values. So if you construct the Hasse diagram for this, so then it will get like this. So if you see this, so phi is subset to A, phi is subset to B, pi is subset to C. Next, A is subset to AC, so the C is subset to AC, B is subset to AB, B is subset to BC. So like that we can finally this is ABC will become the superset for all. Next, upper bounds and lower bounds. So from the Hasse diagram, we can identify there are some elements that are called as upper elements and the lower elements. So if you see there, the upper element means, in another word, in another way, you can simply it is say it's a greatest element, which is going to be the element without any, so the element succeeding all other elements. Okay, in the simple way, I can say that is, this is the element which is succeeding all other elements. That means the elements will be there on the top in the diagram. Okay, if you see this one, so these are going to be your upper bounds, and the lower bound means, so the element that precedes all other elements. Preceding means starting element. So here this is the lower element that we are going to consider, that is going to be the lower bound. Okay, now here this upper bound, lower bound, we are going to discuss or refer with respect to the set. Okay, let us, with respect to the set 5, the upper bounds are 1, 2, 3, and lower bounds are 6 only. Like that we can say. And from this I can identify greatest lower bound and least upper bound. Okay, whenever we have multiple values, see the previous example. In the previous example, we have for the set 4, 5, we have 1, 3, 6. Now these three are the upper bounds. Among these three, the lowest upper bound is 3 only. Now that becomes your lowest upper bound. Similarly, we can identify the greatest lower bound. Okay, now see this example directly. So let us see here with respect to the set BDG. Here we have the BDG. With respect to this set, we are going to consider the upper bound and lower bounds. Okay, so here G becomes your least upper bound, and this is the least upper bound, and B becomes your what we can say that is the greatest lower bound for this one. So next lattices. Okay, what is actually this particular lattices? So it is nothing but your partial order relation or partial order set, which contains for every pair of elements, if it contains greatest lower bound and least upper bound, then that particular partial order set is going to be called as a lattice. Okay, we have the partial order set or partial order relation. In that relation, for every pair of elements, let us A comma B becomes every pair of elements. If you have greatest lower bound and least upper bound, then that is going to be called as a lattices. Okay, here if you see this, the least upper bound can be represented as a join operation between the two elements, and the greatest lower bound becomes it will be treated as a meet operation with respect to this lattices. And here these are the examples for this one. So this is the lattice where for every pair of elements we have upper bound as well as lower bound. But whereas here, let us if you consider this FE, for that there is no upper bound, so that there is no least upper bound, so that it is not possible here. So that's why it is not a lattice. And this is regarding the properties of the lattice. So if you see here, we have four important properties are there with respect to the two operations, that is a meet and join operation, which we considered previously. So idempotent law, so which is defined between the two values, we need to get again same value. Okay, a into a meet a, again we'll get a. Okay, b meet a means a meet b means it becomes your commutative law. Next, a meet b meet c equal to a meet b meet c, then it is going to be treated as associative law. And here a meet b join, sorry, a meet a join b, that equal to a, so now it is going to be treated as a absorption law. So the same thing we can apply on join operation. A join a equal to a join b equal to b join a join b join c equal to a join b join c. So a join a meet b equal to a. So this is absorption law. So these are the important properties that we can consider with respect to a lattice. And coming to the last topic for today, so that is functions. Okay, very important one. Let us see what actually this particular function is. Okay, let us will assume that there are two sets are there, x and y. There are two sets, and we are going to define a relation from x to y. Okay, so the relation is defined in such a way that for every x belongs to x, there is a unique element y such that x comma y is a ordered pair in the relation. Okay, that means for every element in the first set, there will be a mapping in the second set. Okay, so then unique element is mapped in the second set, so that is the important property. So then I can say that that relation becomes your function. So that can be represented in the form of the condition. Okay, so for every x belongs to x, that must be related with some y, and that particular y must be unique for every value whatever we are considering here. Okay, so the domain of f must be x, and not it is not subset of x. That means domain of x, for the given relation we will consider the domain. That means it should contain all the elements from set A or from the set first set. That means every element in the first set should be mapped with at least some element in second set. So let us say similarly the second property is uniqueness. Okay, so there should not be same element that will be mapped with this first set like that. And this is the example. Let us x equal to 1 2 3, y equal to pqr. Now here if you are going to represent in the form of the relation, it will be like this: 1 2 3. 1 is mapped with q, 2 is mapped with p, 3 is mapped with R. That means every element is mapped with unique element in the set Y. Now it is going to be treated as a function. Now here this is the important point. So how many how many number of functions are possible from set x to set y? If set x is containing m elements, set y is containing n elements. It is given by n to the power of m. Okay, let us see here. This is actually both are 3 3. Let us set x is 2, set y is containing 3 elements means. So now 3 square possible. So from set x to y. Okay, if you are mapping the function from x to y, then it will be 3 square. That means 9 different 3 square means 9 different types of functions are possible that we can define from set x to y. Next, domain and range. Okay, so here if you are creating a function or if you are mapping a function from set x to y, so the set x is called as a domain and set y is called as a codomain. Okay, and this codomain becomes the range in range sometimes. If all the whatever the element that are mapped from the set x, they if you are going to group them in that particular set, then that becomes your range. So see here the range can be defined like this. For some x in x, f of x equal to y. That means whatever the element that is mapped from set first set to second set, only if you are going to group them, that is going to be your range. Let us see this example, you may get clear idea. Let us f of x equal to this is yeah, x into 2 plus 1. Actually it is x square, I think it is x square plus 1, and these are the values. Now if you this becomes your domain, and if you apply this particular function, we'll get 5 to 1 to 5 only. Okay, now this 1 to 5 we will get it as a range. And these are different types of function that we can define. First one, one to one function. It is also called as injection function. So if you are going to map distinct element of x into the elements of y, then it is going to be called as one to one mapping. Distinct element of x is mapped to distinct element of y. So let us see here, 16 is mapped with 4, 4 is mapped with 2, 9 is mapped with 3, so that it is become one to one function. Here if you see this, it is not one to one. Why? Because minus 2 2 both are mapped to 4. Now it is not going to be a one to one function. So next one, onto function. It is also called as surjection function. Okay, so here if each element of y is image at least one element of x, that is from set x, so then I can say that that is a onto function. Now, what is simply I can say that every element of set second set should be mapped with at least one element from the first set. So then I can say that that becomes a onto function. Let us see this example here. Here we have two elements AB. AB is mapped with the elements from set 1, 2, 3. But here if you see this, in the second set we have A, B, C. But C is now not mapped with any element from set. So it may be a function, but it is not a onto function. But here it is a onto function. Next one, bijection function. So the function which is both one to one and onto. Okay, so which is following both the properties one to one and onto, it is going to be called as bijection function. Here I can we can consider example for this. So this is a bijection function example we can consider for this. And this is the important points with respect to the types of three types of functions what we discussed. We may expect questions on this one. Let us see here. First one, all this is regarding how many number of functions are possible. Actually initially we discussed one point, that is a number total number of functions that are possible from set x to set y is given by n to the power of m. Okay, here this is the last formula we consider. Okay, this is actually a function, but here with respect to the type of function, how many functions are possible? Let us see here. We have the set x with the m elements, set y with n elements, and if you are going to if you want to find out how many number of one to one functions are possible from set x to set y, it is given by ncm into m factorial if n is greater than or equal to m. Okay, if n value is greater than m, then this is the case. Suppose if n value is less than m, then it becomes 0. Similarly, the number of onto functions that are possible from set x to set y with the same m and n elements is given by summation of r equal to 1 to n minus 1 to the power of n minus r into ncr into r to the power of m if m is greater than or equal to n. If m is less than n, so then it will becomes 0. See here, here we considered first n value, but here we will consider m value as the first. Next, third point here, this is regarding one to one onto. Okay, that is a bisective function. How many number of bisective functions are possible from set x to set y? It is given by n factorial if m is equal to n. Suppose if m is not equal to n, then it will becomes 0. And coming to the another point, so this is also like with respect to onto function, but the number of elements from the set x is m, in the set y is only two elements. Okay, second set contain, if it is containing only two elements, so the number of functions that are possible, onto functions that are possible is given by 2 to the power of m minus 2. And coming to this onto functions, again the set x is containing m elements, set y is containing 3 elements. So then the number of onto functions that are possible is given by 3 to the power of m minus 3 into 2 to the power of m plus 3. So these are the formulas, or so this may be shortcuts that you have to remember whenever you are working with that. Next, this is the identity function. Okay, it is very simple. If the same element is mapped with again for the same, that is if f of x is mapped with to x once again. Okay, if f of x is equal to x, that means x is mapped with x once again, then I can say that it is identity function. We may found like elements values like this. And composition of the two functions. Actually, this is one of the operations that we can apply on the functions. So that is the composition of composition, and we will represent like this. Let us, the function f is mapping from x to y, and the another function g is mapping from y to z. So here the composition should be possible if we have the mappings like this only, x to y, and this is from y to z, then only it is possible. Okay, so then if we can map from f to z, we can apply this composition between f and g functions, and it is represented as g circle f. So g circle of x is given by g of f of x, and given two functions f of x and g of x, we can easily identify g circle f of x equal to, so we can identify this. And this is another important type of function, inverse function. Okay, any function if it is mapping from x to y is said to be invertible when it is possible, means if f inverse is a function from the range of f into x, that means if you are going to consider again, so if it is possible to map from y to x again, so then we can say that that function is invertible function. Okay, so that means x to y is by default possible. Again, if it is possible to map from y to x, range from the range means y is the range from y to the x, if it is possible to map the elements, then I can say that that is a invertible function. And this is the function we can say example for that, which comes under for example as invertible function. So normally given f of x equals some 2x plus 3, if I want to find out f inverse of x for this one, so normally what we'll do there is we'll consider y is equal to x plus 3, we will make 2x plus y minus 3 x equal to y minus 3 by 2, and this f inverse of x is given by x minus 3 by 2. So we will replace this x y with x and we'll write like this. So like this we can find out inverse function for the given one. Okay, so this is regarding today's session. Okay ma, thank you for listening for you people. Thank you ma, love you, thank you.